Uh, in today's video, we are going to look into the aspect of entropy uh, in deciding the spontaneity of the reaction. Basically, what we are trying to understand is what are all the pros and cons of using entropy as a criteria for spontaneity. So when we look into entropy in a spontaneous process, like the criteria for spontaneous process in general, if we talk about, we know that there are two important criteria that decides whether whether the process is spontaneous or not. One is the criteria of having a minimum internal energy, minimum energy of the system. Then another criteria was maximum entropy. And minimum internal energy, we know that there are certain anomalies here because some of the processes which were endothermic was also spontaneous. So that's why it had its own failures. However, when it comes to entropy, uh, there was no such issue. Whenever you have a process where you have the change in entropy to be positive, it is a spontaneous process. Okay, so that is the important advantage of using entropy as a criteria for spontaneity. So whenever you have the change in entropy positive, it means that the process is spontaneous. However, there is a drawback of using entropy as a criteria for spontaneity. What is the drawback? Because if you remember the previous videos, if you have gone through, you know that the delta S is usually, according to definition, is a sum of system and its surrounding. Or in other words, we are usually considering delta S universe. Okay, so that means here, when you are looking at entropy as a criteria, you have to look into the changes both in the system and the surrounding together. Okay, and we know that practically it is not a very convenient thing to do because you cannot limit the surrounding, although you can approximate to it to be the immediate surrounding, but it's not very convenient for us to decipher the totality of the entropy change in both the system and the surrounding. It won't be giving us any exact values. So that means it's for practical reasons, entropy as a criteria is not a very useful criteria for determining whether a process is spontaneous or not. So, and if you remember, when we tried to look into the entropy in both reversible and irreversible process, we also looked into a case where we considered only system. Okay, if we consider only system entropy, okay, we found that in order to use entropy criteria for a system alone system, it is mandatory that these two state functions to be constant, that is the internal energy as well as volume. And we know that for all the practical purposes, this is not a very convenient thing to do. For example, we rarely do any chemical reaction at a constant volume, because when we do a chemical reaction, when there is a change in state of the reactant and the product, there is volume change you can expect. Suppose you start with a solid reactant and when it changes to the product, it becomes gaseous, then the volume will change. So that means you cannot keep the chemical reaction volume as a constant factor. So that's why this is not very practical. Though you might imagine that, okay, at constant temperature, you can keep the internal energy constant, but this is not always the case. Though you might be thinking that internal energy might be constant, but it's not always the case. For example, if you take into consideration phase changes, for example, a matter changing from solid to liquid, we know that it happens at a constant temperature. But we know that though it is happening at a constant temperature, the internal energy is not constant because the phase change is happening from solid to a liquid state, and the internal energy will increase correspondingly. So that is why if you are wanting to take system alone, you have to consider a process where the internal energy and volume is very, very constant. And that is not practically possible. So that is the major drawback of the entropy as a criteria of spontaneity. Though it is a very absolute criteria, because whenever there is no process, whichever process is spontaneous, will have the delta S to be a positive value. Okay, but the practicality is not good, because here, whenever you're talking about change in entropy, you have to consider both the system and surrounding together, and that's not always practical to do. Okay, so these are some of the pros and cons, mainly two, one pros and one con of this using entropy as a criteria. So that means we require a new state function, which if we are determining its property in the system only, it should be able to give me, okay, this process would be spontaneous or not. So that led to the discovery of another state function, and that function is referred to as the Gibbs energy. And this Gibbs energy is also referred to as the Gibbs free energy, or free energy in as free energy also it is called. Okay, so that is what this function is very, very useful. Where the entropy criteria fails, this criteria takes has a great advantage, and that is why uh, uh, this criteria, this particular state function is very, very important. Now, mathematically, when we talk about the Gibbs energy, you can write Gibbs energy as G equals H minus Ts. Okay, this is what mathematically it means, and we know H is the enthalpy, T is the temperature, S is the entropy. So mathematically, it's related like this. So if we talk about finite change, okay, suppose a change in state is happening from one state to two under isothermal conditions, then delta G simply would be G2 minus G1, because G is again a state function. Now, G2, you can write it as H2 minus TS2. Now, why I didn't write T1 here? Because temperature is constant during the change in state. And G1, you can write it as H1 minus TS1. Now, I can bring the enthalpy terms together. So it should be H2 minus H1 bracket closed. Then minus TS2, this would be plus TS1. Now take a minus T out, it should be S2 minus S1. Okay, so you can write delta G to be, now H2 minus H1 is simply delta H, and S2 minus S1 is simply delta S. So this is the expression for finite change in the Gibbs energy at an isothermal condition. So at isothermal condition, this is the expression for finite change of the Gibbs energy, which is related to the delta H and delta S through this particular equation. So this particular equation you have to keep in mind. That's all for this video. We'll talk about in the next video the further details. Thank you.